Okay. All right. Hello, everyone, and welcome to today's NetBlaze seminar. And we're very happy to have Martina from Max Planck Institute for Intelligent Systems, Germany, here today to talk about relaxing conditional independence assumption in networks, the case of communities and reciprocities. So the time is yours now.
Okay, perfect. Thank you. And thanks everybody for being here today, and a special thanks go to the organizer for building also these communities and giving me the opportunity to present my work. And today I will be talking about one of the main research area I've been tackled during these years of my PhD, and is about relaxing conditional independent assumption in networks. And I will present two projects that will consider two properties of networks, like communities and reciprocity. And before starting, I will just present myself. As Anlin said, I am a PhD student at Max Planck Institute for Intelligent Systems in Tübingen, which is a very cozy and small village in the southwest of Germany. And I'm part of a group named Physics for Inference Optimization, supervised by Caterina De Bacco. As the name spoiler already, this group is divided in two subgroups. So there are people working on routing optimization on networks, which means they try to develop models to optimally move mass from sources to sinks. And instead, another part works on or with inference of networks. So what we try to do is like we try to describe networks through probabilistic models, and we try to extract parameters, model parameters that should be capable of describing the system we are observing, and also helping us making future predictions. And I'm part of this subgroup, and today I will describe a bit the research I've been working on the last 2 years. And the starting point are community detection algorithms. So these are special tasks that can be performed on network when you work with inference of networks. And the main assumption with this approach or with this method is that given a network like here, we assume that there exists an underlying pattern that drives the way people or general nodes interact between each other. And in other words, we can say that the probability of an edge depends on the community of its node. So what a community detection algorithm tries to do is, given a network and assume this underlying structure, we try to make inference and retrieve a partition of the network according to the communities we impose in the latent variables. Of course, there are plenty of ways to derive communities, and generative models is not the only one, but maybe all of you know modularity, optimization of const functions. But yeah, today we will focus on these generative models because also these are my main focus. And so these models are very popular, very efficient, and they are able to not only retrieve communities, but also they allow, since you pose a probability distribution, they allow to perform edge prediction. And in addition, they are generative models. So once you infer the parameters, you can also use them to generate samples that hopefully are similar to the input data. And this exactly comes the problem, because the problem is that they fail to reproduce some network properties, like, for example, reciprocity. We focus on reciprocity because it's a property very useful for anthropologists or sociologists, and we collaborate with like more sociologists and anthropologists, and they use this kind of community detection algorithm, but what they notice is that when they try to reproduce sample network, they saw that the reciprocity computed in the sample network generated with the community detection algorithm like MT or BMF, the reciprocity on this sample is way lower of the true reciprocity of the data. So here we have synthetic data with higher reciprocity as higher is alpha, and you see that multi-tensor or Bayesian post-symmetric factorization methods are not able to reproduce a sample network which reproduce these network properties, like, for example, reciprocity. So this was the motivation of also my PhD. And so now the question is, how do we solve this problem, right? So again, we can focus on many network property like triangles, or maybe not communities, but I don't know, property like average degree or sampling or whatever. But for us, or at least for me, in my experience, these are the two properties I will consider today and have been considered in the past. So we have community structure on one side and reciprocity on the other side. So reciprocity, again, is the tendency of a pair of nodes to form mutual connection between each other. And so you understand that now we just talk about directed networks because reciprocity only appears when we have directed connections. And these are two properties, but they can be thought also as mechanisms that drive the way people interact with each other, because they can interact because they belong to the same communities, or also because I help, I don't know, Han-Lin, and then Han-Lin is more prone to help me as well. And but in the past, these two problems have been tackled separately. So as I said, for community structure, there have been generative models with latent variables. And instead, for reciprocity, or at least reciprocity, have been encoded in exponential random graphs. So generative models from one side, they are not able to reproduce like network properties like reciprocity, but on the other side, the exponential random graph don't allow to incorporate in the model latent variables like communities, for example. And our assumption is that for us, it's reasonable to expect that the mechanism that regulates the existence of interaction can be influenced by both the pattern of communities and reciprocity, because as I said, even if we don't belong to the same communities, we may interact just because there is a reciprocity relationship between us. And given this assumption, of course, now we would like to develop a model that encodes this assumption and hopefully will allow us to reproduce network sample with more reliable and closer to the real data. But to do this, the first step is to break the conditional independence assumption. So if you're not familiar with this, the conditional independence assumption is given by the following formula, where we assume that every edge in the network is independently and identically distributed according to a distribution P. So which means that every edge is independent from each other. And this assumption has been used a lot and always, actually, because it helps the computations. And but now, I mean, we cannot use this condition independence because we want to model reciprocity. And by definition, reciprocity encodes the tendency of a person to form mutual connection with another person or node in general, of course. And so we cannot model the marginal anymore, but instead we need to relax it, at least to consider the two edge joint distribution, because with the reciprocity, we are saying that the fact that there exists an edge from node I to node J depends from the existence or not of the edge from the other side. And we can write, of course, this joint distribution, probability distribution, as the product of conditional and marginal. And now, with this introduction, I will move on to two models that follow two different approaches, and I will present them as I developed during my PhD. So the first approach is to consider only the conditional distribution, or not only, or let's say starting from the conditional distribution. And what does it mean? It means that we encode the assumption that I've just presented to you in the conditional distribution. So we are saying intuitively that the probability of observing an edge from node I to node J depends, of course, on the latent variables, but also on the fact that exists or not the edge from the other side. And we model this as a Poisson distribution, also because it helps with the mathematical computation, and in this case is also easy to interpret. And where do we encode our assumption? Where we encode them in the mean, so in the parameter of this Poisson distribution, that is the mean. And we are saying that the average of the interaction from node I to node J depends on two effects, like we said in the assumption. So the number of edges may depend on the community effect, but also on the reciprocity effect. Because here we are saying that we can observe the average number of edges from node I to node J, like are given by how or where the nodes belong to, and how the community, the nodes belong to, interact together. But this can be increased also from the fact that we observe the edge on the other side. So the reciprocity effect is already modeled, where eta is the reciprocity parameter, and to model instead the community effect, we use like the formulation already used in the Bacco et al. In 2017, where basically they describe this multi-tensor, which is a mixed membership community detection algorithm. And since we are modeling the directed network, we will have matrix U and matrix V to model the community membership for the outgoing and the incoming edges, and also an affinity matrix W, that describe how communities like interact to each other. So if this matrix is mainly diagonal, means that the structure of the communities are assortative, or if it's higher on the diagonal, means that they are disassortative. Okay, so this model is called CREP, and it has some properties. So first of all, as I said, we have an additive contribution between communities and reciprocity. So the reciprocity can only increase the expected number of edges from node I to node J, and also because eta can be only positive. But the main drawback of this model is that we were not able to write or to specify a marginal distribution, because this will require to specify consistency between conditional and marginal. And this in general is a difficult task, but we didn't want to give up, and then we use a pseudo-likelihood approximation. So which means that we approximate our joint likelihoods through the product of the conditional. And once we specified and we have this pseudo likelihood, we can maximize and optimize it through an expectation maximization algorithm. That it's an iterative algorithm that at each step try to maximize the pseudo likelihood through expected values. And it is also efficient, scalable, because exploits the sparsity of the data set. So you understand that every time Aij is 0, then this, of course, is not counted, and this speeds up the computation. Without going too much into the details, I jump to the results, and I started showing you the same plot I show you at the motivation, because here I added the points regarding three versions of our algorithm. And you may notice how the reciprocity computed on the sample network generated by our algorithm present a reciprocity much closer to the reciprocity of the input data. And in addition, if we focus on the edge prediction, we notice also that, okay, the CREP performs as good as the standard community detection algorithm like MT. But in addition, now we have access also to the conditional expected value. So we are able to compute the conditional AUC. And we notice how when reciprocity is higher, then the conditional AUC brings much boost the result, because you use much information, more information to compute this prediction, of course. And yeah, here I didn't mention, but the networks are generated with the different value of reciprocity now are given by this eta parameter here. And when eta is higher, also the contribution of the communities is lower. Yeah, to conclude this part on CREP, I just present an additional results on a real data set, in particular on the Erasmus Exchange Network, because this model gives us also the possibility to quantify the contribution of the communities and the reciprocity in each interaction. Indeed, with this CR ratio, we are able to compute the contribution of the communities for the edge from node I to node J. And then when we consider the true contribution in the true direction and we make the difference, then we have this value, Dij. And based on the value of this Dij, then we can infer how a given node behaves. So for example, here we have 4 different ego network examples taken from, of course, the Erasmus Exchange Network, because where these, so here nodes are universities. And we presented these 4 cases because they have 4 different behaviors. And for example, here on the top left, we have the University of Sevilla, if I'm not wrong. And we see that the color is mostly red of its interaction, which means that the Dij is lower than 0. And which means that this CR ratio from Ij, it's lower than the CR ratio from Ji, so from the incoming edges. So which means that Sevilla tends to send students just for a reciprocity effect, while the other university sends students to Sevilla for a community reasons. And in opposition, we have the other case of Munich, where instead the interaction are mainly blue, and which means that Munich tend to choose the university according to the same communities and send students to them, while instead those universities send back students just for a reciprocity effect. When these two CR ratios are similar to each other, we have mainly white interaction, like the case of Florence. And but of course, this is a special case we found in the Erasmus exchange network, and other cases are where we have like mixed interactions. So to conclude this part, I just summarized that this was the first attempt to present a model with community and reciprocity effect, and it gave good results both in terms of sample network and also in terms of edge predictions. And in addition, it allows us to estimate the relative contribution of community and reciprocity in determined edges. But as I said, we don't have a closed form joint distribution, and we made use of a pseudo-likelihood approximation. So we would like to improve on this. And in addition, we also noticed that in networks where reciprocity play a bigger role, CREP poorly performs in terms of recovering communities. So that's why the model that I'm presenting now, following a different approach. And in particular, we try now to model directly the joint distributions. So this model is called joint CREP. And what it tries to do is like, it tries to break the condition independent assumption by modeling directly and jointly the edges of the same pair of nodes. So again, what we want to try to do now is modeling this joint distribution without any kind of approximation. So for this, we use bivariate Bernoulli. Sorry, and bivariate Bernoulli is a distribution that allows the two variables, in this case Aij and Aj, together to have 4 different values. So both of them can be 0, one of them can be 1, or both of them can be 1, 1. And here I wrote it in as an exponential family form where Fij and Jij are the natural parameter of this distribution. And now again, we need to find a way to encode the assumption of our model that again are given by community structure and their reciprocity. There exist many ways, but we chose to model the natural parameter. And in particular, we model the natural parameter that depends only on the single edges in relationship with only the communities, while instead for the parameters that here is Jij, that is the, I didn't say before, sorry, it's the pair interaction parameters. That is the only parameter that put together the Aij and the Ji. And of course, in this case, then we put a relationship together with this eta parameter that somehow it's model the pair interaction parameters. And of course, there is a relationship between this natural parameter and the probability of the model. And intuitively, we can see how the probability of having only one edge depends only on the communities of these two nodes, while instead the probability of having both edges, yes, depends on the community structure, but also on the pair interaction parameters. And this is a different model, and from before, of course, we cannot model anymore weighted networks, but we can model only binary networks. We don't have an additive contribution anymore, but we have a multiplicative like contribution between reciprocity and communities. But now, since eta is the argument of a logarithm function, we can notice that when eta is between 0 and 1, we have a negative value for these pair interaction parameters, which means that now the reciprocity can also decrease the probability of observing the edge from the other side, something that with CREP was not possible, for example. And In addition, we may use also the properties of the bivariate Bernoulli, which put in equivalence the uncorrelatedness and independence. So which means that when eta is equal to 1, then Aij and Aji will be independent from each other. And the joint is just the product of two Bernoulli. And in addition, the bivariate Bernoulli has the nice property that every distribution is in clone form, and both the marginal and the conditional still Bernoulli. And once again, this is a model with an exact two-edge jointed distribution, and we don't need approximation to perform the inference. In this case, we still use an expectation maximization algorithm because we found a closed form equation for the updates. And again, I'm not going to the details, but I jump to the results, showing synthetic data first, where here R is the reciprocity on the synthetic data, and higher R, higher the reciprocity of the data. And we see that joint CREP is also very good in retrieving in reproducing sample with the reciprocity very close to the one of real data. And as well, joint CREP is good in edge prediction. In particular, we see how it improves CREP in terms of marginal AUC, retrieving the good result of standard community detection algorithm, and it performs as good as CREP for the conditional AUC. But what joint CREP improves is the recovery of communities, especially when reciprocity plays a role, like I said before, where we can notice that CREP drops its performance, while instead joint CREP constantly perform as good as a common standard community detection algorithms. Sorry. And to conclude, I just show a real case where we have the high school network, and we fit the different models to infer the parameters. And once we have the parameters, we try to reconstruct the high school networks either through the marginal expected value or the conditional expected value. And we see how the conditional expected value brings better results. And in particular, the reconstruction of joint CREP is more precise, closer to the real data, because it does not add so many edges like CREP. And also the intensity of the edges, showing here with the black, describe that joint CREP uses or predict with higher probability, especially the interaction that are reciprocated, differently, for example, from CREP. So with this, I'm going to conclude. Just remind once again that doesn't exist a true model, but these are just, I just wanted to present the journey I've been taking during these 2 years, starting from a common and standard community detection algorithm, moving to a model that jointly uses communities and reciprocity through an approximation, and then improves one more this model to account also for closed form of the joint distribution. But as I presented here, they have all different properties, and according to the application at hand, ones would like to use one model with respect to another. And with this, I thank you for your attention, and you can find the references for the two models I presented here. And also you can play with the code. It's all free and available, and you're welcome to use it. Thank you again. And if you have any question, I will be happy to answer to them.
Thank you. Thank you, Martina. Thank you for this great talk. And is there any question from the audience?
Sorry if I took too long.
No, it's good timing. Any questions? I have a question, actually 2 questions myself.
Yeah.
First, this is community detection on a directed graph.
Yes.
Right. So how do we define a community on a directed graph? Because usually, if we're talking about an undirected graph, then the connection between 2 nodes in the community will be higher than the inter-community connection. So for a directed graph, if we need the both direction connection between 2 nodes, or we can only have one, how do we define here? Yeah.
Yeah, exactly. And so here maybe was not super clear that we use a mixed membership model for modeling the communities, which means that we have overlapping communities. So again, the distinction between highly dense inside the network and less dense between network is not so sharp as when you're considering hard membership. And the model, the multi-tensor developed by Debacco, is so since we consider directed network, we have 2 different matrices for the communities. So the matrix U, which which output the communities when we consider only the outgoing edges.
Oh, okay.
And the matrix V, that are instead the infer communities only when we consider the incoming edges.
Okay.
Because there are situations when you may have 2 different communities according to the outgoing or the incoming.
Yeah.
So it was important to distinguish the 2 of them. So in the simple case, the one of multi-tensor, then the expected average of interaction from node I to node J depends on the outgoing communities of the node I times the incoming communities of node J, and how these 2 communities interact to each other. And again, W is free, so it's not always the case that communities are more densely connected inside each other, because W can be also disassortative, and so the structure of the network is disassortative, which means that the communities tend to interact more among each other than inside each other. So it's really free as a model, and you just infer everything from the data.
Okay.
Maybe I confused you, but
it's interesting. I mean, it's a bit different from my little restricted knowledge on the community detection.
Yeah, it's more general as an approach. That's why also generative models are more powerful somehow. For some application, you need this flexibility. So that's why.
And I have a more detailed question related to some technical details, maybe. Can you share the slides again on the page, I guess,
sure.
on the pseudo likelihood or pseudo probability?
Yes.
So the difference between this pseudo probability is like the actual probability you need to P Aij given Aji theta times P
the marginal
Aji, right? So why this approximation is works? I mean, you simply delete a marginal, and why it's still approximation?
But I mean, we didn't invent this approximation, of course. It has been widely used also in the physics community, where it's very difficult to find consistency between marginal and conditionals. So it's just a well-known approximation that like works in this case.
Oh, okay.
Yeah, otherwise you always need to find consistency between conditional and marginal, such that the joint is also probability distribution.
Oh.
That's why it was not possible in that case.
Okay.
And even if okay, you find a way to make it possible, then it's very difficult to know the distribution of the joint. So, for example, now in this case, we pose a Poisson distribution on the conditional, but then if also the marginal is Poisson, then the product of two Poisson is not Poisson anymore. So you don't know the form of the distribution of the joint.
Okay, thank you.
No, thank you.
For explanation, thank you. Any other questions?
I may have one, if you can hear me. Yes.
Yeah. Yes.
Yeah.
Oh, actually two. Sorry.
No worries.
From the first part, when you said that like the mean of the Poisson distribution, yes, exactly, is composed by a community effect and a reciprocity effect. I mean, just a curiosity, can the two be correlated in some sense in real data? I mean, not in the model.
Yeah, I assume they can, because you tend to interact with people in your community.
Yeah.
So yes, they can. But I mean, there are also cases when you have only one of the two, for example. So you may notice an interaction only because of the reciprocity effect. If I think about maybe citation networks, maybe I tend to collaborate back with another or old collaborator, even if we are into different fields. So imagine that the communities represent the fields, and okay, we may not interact because of that, but we interact maybe because, I don't know, I got a collaboration with the person X from the other field, and then this person X tend to work with me again, even if we are from two different communities.
So in that case, will be like two separated, like there will be just reciprocity. No? Okay.
Yeah, I mean, there are these two extreme scenarios. Yes.
Yeah. Okay. And thanks. And the second one was about the second part.
Yes.
And like in the second part, you are considering like binary network, no, where the edge can exist or not.
Yes.
And this is also because you are choosing a bivariate.
Yes.
But you can relax this assumption by choosing another distribution that it is a bivariate but non-Bernoulli one.
Yes, but I mean, I chose this because the bivariate Bernoulli has nice property, like everything is in closed form, so marginal, conditional, and yeah, I don't have the results here, but also in the paper I show how, you know, you can use all the three distributions. So you can use the marginal, you can use the conditional, you can use the joint itself. So this is very powerful. If I don't know, I use again a Poisson, a bivariate Poisson, then maybe it's not in closed form, and I have problem to retrieve the marginals, and the marginals are useful, especially for computing the link prediction, for example. Like here, I mean, when I have marginal AUC, means that I predict the existence of an edge through the marginal expected value. And if I don't have the distribution in closed form, then it's difficult to recompute it.
Yeah, okay, understand.
For CREP, we derive the formula that is consistent with the conditional, but it's not always super easy to find that.
Yeah, of course. I mean,
but,
one put himself in a condition that can actually do things.
Exactly. It would be ideal to have the best model ever, but I said in the conclusion is not, I mean, the freelance theorem, right? So everything is right and doesn't exist the true model for everything. So that was also, I described it like that. Also, the way I thought through the process of like the PhD, and I didn't say, but these two papers have been done in collaboration with the postdoc Alicia Sardaria and Caterina De Bacco, my collaborator, and we are kind of working together to try to solve this huge problem, going step by step, and every time solving a problem more. But
you had a piece.
Yeah, exactly. And then every time, even if the piece seems very small, then all the implications that you need to solve are way bigger. So
yeah, no, I can fully understand. Yeah.
Okay, any other questions? Okay. Sorry?
No, in case everybody can reach me either by email, the contact are all in the first page of the slides. So in case I can share to them.
Right. Then if we don't have any questions, then thank you again. Thank you very much for this excellent talk today. And this video will later to be uploaded on the YouTube. So I guess we will see you again in the week after next week.
In 2 weeks. Perfect.
Thank you. Thank you again.
Thank you.
Bye-bye.
Thank you.